There we go. Okay, hi guys. So this is the pre-lab talk for exploring gas laws, and all of these are related to something called the ideal gas law, PV equals nRT. And all of this is just the pressure, volume, moles, ideal gas constant, and temperature, and how all of these are related. The important thing is that the units you use for your ideal gas law will depend on the units of your gas law constant. So if we look at these two, they have different numerical values, but that's because they're in different units. Both of them are in liters, moles, and Kelvin, but they have different pressure units. And there's lots and lots and lots of different R values for different for different unit combinations. These are the two most common. These are the two that we'll provide you for this class for you to convert to in between. And so in this case, you will usually have pressure in atmosphere or torr, or you'll need to convert it to that to be able to plug it in. Volume would be in liters to match our units. Moles would be in moles. The big one is temperature must be in Kelvin. Regardless of what you're looking at for any gas law question, temperature must be in Kelvin. There really isn't a way to get a reliable R value using a temperature in Celsius. All of them are defined with the temperature in Kelvin. So make sure you can convert between Celsius and Kelvin. It's really easy. You just take your temperature in Celsius, add 273.15, and now it's your temperature in Kelvin. Something important to note is this is an ideal gas law, so there are some things that it doesn't account for. And those two major things are molecular interactions. It assumes they don't interact. And molecular size. It assumes that the molecules themselves don't actually take up any volume. So there are real gas laws that take these into account, like the van der Waals equation, but they are much more complicated than the ideal gas law in terms of doing the math and trying to experiment with them. So if you want to look into them, go for it, but we're not going to be messing with them for this experiment. The first new thing that we need to talk about with this is how to measure pressure. Volume we've measured, temperature we've measured, moles we've calculated or measured indirectly. So pressure is the only one we haven't really dealt with. Again, if you were in lab, there's a barometer on the wall. You could walk over to it, take a reading just like from glassware. You measure in between increments, round to the right number of decimal places, and everything's easy. Something interesting to note is a lot of barometer pressures, especially older ones, are in millimeters of mercury. They're measuring basically a distance of mercury somehow as a pressure. Where this comes from is the first barometers basically were a bowl with some mercury in it. And as atmospheric pressure pushed down, the mercury would move up into the tube. And so what they would do is they would measure from the height of the mercury to the height of the mercury in the bowl. And that distance, they would measure in millimeters. So it was called millimeters of mercury, or that height of mercury, and they related that to pressure. So that's why you see these millimeters of mercury numbers referenced here. There are lots of pressure units. There's pascals, kilopascals, atmospheres, torr. We talk about non-metric. You have pounds per square inch or PSI. So there's lots and lots of options. And you can convert between all of these different values. Atmosphere is the most commonly used one at this point. It is defined as the pressure of Earth's atmosphere at sea level. And so there's all of these different pressure conversions to get between the values you need. And so those will be important plugging into the ideal gas law. But the ideal gas law is actually created later, after a bunch of named gas laws like Boyle's law were found originally and put together into the ideal gas law. And I'll show you how we can take the ideal gas law and break it down backwards into some of these named gas laws in a few slides. So Boyle's law, all of the named gas laws rely on certain measurables being fixed. So Boyle's law has a fixed amount of gas, so moles is constant, at a constant temperature. So the only thing varying is pressure and volume. And what was found is as pressure increased, volume decreased, and vice versa. And the easiest way to think about this is if you have a sealed syringe with a plunger on one side and the hole on the other side where you would either push liquid out or put a needle or something, if you cap that, as you press down, you're applying more pressure. But the volume in that syringe is getting smaller. So as you increase your pressure pushing down on the plunger, your volume gets smaller and smaller and smaller. So that's what it's talking about, meaning inversely related. As pressure goes up, volume goes down. And so the equation for that is P1V1 equals P2V2. And if we were to take some arbitrary numbers, we had, let's see, pressure of 10, and a volume of 10. Let's just use some easy numbers. If we increase that pressure to 20, what does our new volume become? So this is just 100 x equals 5. So pressure, volume. Our initial pressure was 10. Our final pressure was 20. Our initial pressure, or our initial volume was 10. Our final volume was 5. So as pressure went up, volume went down. So you can, again, plug in arbitrary numbers to try and get these trends if you're better with numbers. Some people can just look at these equations and understand how they interact as you change the variables. Some people just memorize it. It's all whatever works best for you. If you're really struggling with it, I have some tricks and stuff that can help. But there's a lot of different ways to kind of help feel through these. Charles' law is very similar. Constant pressure this time and constant amount. Volume and temperature change. And as volume goes up, temperature goes up. They vary proportionally instead of inversely. And this makes sense. If you take a hot air balloon, they create fire under the balloon, and as that air heats up, it expands, which causes the balloon to expand and then float. And that's getting into density. And we can tie that back to the density that we worked on earlier in the semester. So we could do the same thing and plug in some arbitrary numbers, or you can look at it and see as volume goes up, temperature has to go up. Or you can think about it realistically. As you heat it up, that's going to cause it to expand. As you cool it down, that'll cause it to shrink. Gay-Lussac's law sometimes goes by a couple of different names, so don't be thrown off if you see a different name, but it relates pressure and temperature, meaning volume has to be constant and moles has to be constant. And pressure and temperature are directly related. And so let's think about this. Pressure is the number of collisions with a surface. So the more collisions you have, the higher your pressure is, especially in a specific amount of time. Temperature is how fast your molecules move. It's actually specifically related to the average kinetic energy, something you might get into in lecture. So if we think about a container, and it has to be a sealed, rigid container because our volume can't change, so a metal box or something. If we have some gas molecules in it, and they're moving around, they're bouncing, they're hitting the walls occasionally, and now we increase the temperature, and now they're moving faster, and they're bouncing around more in random directions, but bouncing all over the place. They're moving faster, so they're clearing that entire container faster and faster and faster, and you're getting more and more collisions with the walls of that container. So as your temperature went up, you get more collisions because they're moving faster. If you get more collisions, that means your pressure is higher as well. So again, you can plug in arbitrary numbers to confirm that with some numbers. You can think about it realistically. You can memorize it, whatever works best for you. So somebody realized if we take all of these named gas laws, Boyle, Charles, and Gay-Lussac's, all of these can be combined because they're all using the same variables with the same relationships into a combined gas law. And so now you don't have to hold different variables constant. As long as you can measure them, you can see how all of the variables change at once. But the interesting thing to note from all of these named gas laws and the combined gas laws, they're looking at changes in these conditions. So there was a lot of work that went from going from this point and changing conditions and how different measurables respond to the ideal gas law, which is, what do all of the conditions look like at a single set of conditions? Oops. And so that was really interesting. But because the ideal gas law is built up from all of these combined named gas laws, that means it can be broken down into them as well. So if we take our gas law, and again, the ideal gas law is looking at one set of conditions. It's looking at the pressure, volume, moles, temperature at that set of values. So if we're going to change them, we can set up the same equation for all of them. So all of the initial conditions are ones, all of the final conditions are twos. But our ideal gas constant can't change, it's a constant. It's very, very rare for your number of moles to change. Unless you're specifically injecting gas or pulling gas out of your system, it's very difficult for that to change. So let's say, for example, we set up an experiment and we know the temperature isn't changing as well. It's all done at room temperature. No significant changes. So then our temperature isn't changing and it's constant. If we move everything that's changing to one side and everything that's constant to the other side, we can find out something interesting. In this case, it's already done for us. P1V1 is equal to nRT, but P2V2 is also equal to nRT. So that means we can set these two equations equal to each other and get P1V1 equals P2V2. And this is Boyle's law directly. So now we've gotten Boyle's law from our ideal gas law. We could do the same thing if we had different conditions changing. If we had, here we go, pressure, or let's do volume and temperature are changing, but pressure is not. So only volume and temperature are changing. If we rearrange this using algebra, we'll get V1 over T1 equals NR over P. Do the same thing to this side. And again, our equations are equal to the same thing, so we can set them equal to each other. V1 over T1 equals V2 over T2, and we have another of our named gas laws. And we can do this over and over and over for all of the different values to generate those named gas laws from the ideal gas law. So all of that's to say, you can remember and memorize all of the named gas laws and all the different variations, but sometimes that's a lot to memorize. Or you can memorize the ideal gas law, and as long as you're comfortable breaking it down into those pieces, you can create the other gas laws from it. So you don't necessarily have to memorize a whole bunch of information. And so we can get lots and lots of different questions. And the first thing to do is always figure out what gas law you need. So if we read through this, we're given one set of conditions. We're given one temperature, one volume, one pressure, and we need to calculate the moles. So we aren't given anything changing, so we need the ideal gas law, EV equals nRT. And what we find out, we have a pressure, we have volume, we have temperature. Pressure, volume, temperature. We always have the ideal gas constant. We don't have the number of moles, but it's what we're looking for, so we can just plug in and solve. But as I mentioned, all of this matters about the units of our gas constant. So which gas constant do we use? The answer is it doesn't matter, as long as you match your units. So I'll do this question with both sets of units, and what we'll see is we get the same answer. So using R equals 0.0821 liters times atmosphere over moles times Kelvin. We were given a pressure in torr, but our R value is in atmosphere. We need to convert that to atmosphere. We need to convert our volume to liters to match our constant value. We always, always, always need to convert our temperatures to Kelvin. And so we do that. We plug everything in. We get 0.004354 moles. And you can rearrange the gas law so that all of your values are on one side and your moles get left over. So that's using one of our ideal gas laws, constants. We use the other one. The only thing that changes is our pressure is now in torr, and the pressure we were given in the question is actually in torr, so we don't need to convert it. Everything else we did need to convert. And we plug it in and we get exactly the same number. So again, the units you use and the ideal gas constant you use don't matter as long as all of them match. So as long as you can do dimensional analysis and all of your units cancel out, torr cancels with torr, liters cancels with liters, Kelvin cancels with over Kelvin. You're left with 1 over 1 over moles, which is the same thing as just moles, which is why our answer is in moles. If you're not comfortable going from 1 over moles to just standard moles, let me know. It's just some math with fractions, but I can always talk you through it. So again, units matching, dimensional analysis, same stuff we've been talking about all semester. It's the same thing that matters here. And so we can do all of these with all of the different named gas laws, and it just depends on what we're given. So we're told a 20 milliliter syringe at 10 milliliters with a specific pressure and new volume, and we're looking for pressure. So we were given a lot. We were given 3 volumes, 1 pressure, asked to find another pressure. But we were asked to find the pressure at 15 milliliters, and we were told the pressure at 10 milliliters. We don't have any other information for this 20 milliliters. That's just the volume of the syringe. It doesn't actually matter. So we don't care about that 20 milliliters. If you happen to remember Boyle's law, P1V1 equals P2V2, you can just use it directly. If not, we can do the same thing. We know pressure is changing. We know volume is changing. We weren't told that moles was changing, so it's probably not. R will never change, and we weren't told that the temperature was changing. So we can set that up for our before and after. They're equal to the same thing, so we set these equal to each other. And now we have Boyle's law. And we didn't even have to memorize it. We just had to remember the ideal gas law. Regardless of how you get there, once you get to this point, you can plug everything in and solve. If you're struggling with the named gas laws, convert everything to the same units that you would for your ideal gas law. So liters, moles, Kelvin, and either atmosphere or torr, whichever one you want. Again, we have constants for both of these. That's always a good place to start. If you get really comfortable with doing these calculations, just like M1V1 equals M2V2, the units you plug in are the units you get out as long as everything matches. There's only one exception that I'll explain in a minute. So we plug in atmosphere and milliliters. Our milliliters cancel. We're left with atmospheres. Our answer comes out in atmospheres directly. Had this question asked for the pressure in torr, we would need to convert this, or we could convert our original one to torr, and our answer would have come out in torr. But because the question didn't ask for it, we don't need to worry about it. The only thing that you will always have to convert is temperature must always be in Kelvin. It can never be in degrees Celsius. So that's the only one you will almost always have to convert. It's rare to get temperature given to you in Kelvin. But we can do the same thing with Charles' law. We're given a volume and a temperature. We're asked to find a volume and given a new temperature. So if we remember Charles' law, V1 over T1 equals V2 over T2, we plug everything in and solve. And what I did here is I converted everything to liters and Kelvin, like I would if I was doing the ideal gas law, and then converted it back out at the end to milliliters. Again, I could have left this. I could have left that as liters because the question didn't specify what unit, it just said volume. Had it said milliliters, I would have needed to convert. Again, if you're comfortable with these and you just plug in milliliters for V1, it'll give you milliliters out for V2 and you'll get that answer. But temperature always has to be in Kelvin. Regardless of what everything else is in, temperature must be in Kelvin. It cannot be in degrees Celsius. Okay. You do the same thing with Gay-Lussac's law. I know I'm kind of blowing through these, especially moving forward, but they're all just plugging into the equations and solving, or deriving them from the ideal gas law, plugging in and solving. So you can do the same thing. And so again, I want to call your attention, temperature must be in Kelvin, but other than that, you plug it all in and get 2.7 atmospheres. We were given a pressure and a temperature, asked for the other pressure. So this would be Gay-Lussac's law, or we could derive it from the ideal gas law. You do the same thing with the combined gas law. It's all the same. Again, temperature in Kelvin. We get out a temperature in Kelvin. And again, it just says, what is the temperature? Had it said, what is the temperature in degrees Celsius? Then we could convert it by using our same equation. If we're in Kelvin, then we subtract 273.15 and we get negative 113 degrees Celsius. Because this didn't specify which unit, we could have left it as Kelvin and been fine. But again, it's all the same thing. You plug in, you solve, temperature must be in Kelvin. Hope I've said that enough times. And then we can talk about what happens if you change measurements, more than just looking at the equations. Let's say we were doing a whole bunch of calculations and we wanted to figure out the moles of gas in 2 different trials. So one set of conditions, how many moles of gas does it have? Separate set of conditions, how many moles of gas does it have, and how do those relate? So the calculation we would be doing would be, since we're looking at one set of conditions, we would use the ideal gas law. We want to find moles, so we would rearrange to do this calculation. So then the question asks, if we do trial 2, and the only thing we change is we lower the pressure, how does that change the number of moles we calculate? So, for example, let's just pick some numbers. Let's say the pressure in trial 1 was 2. We don't care about the rest of it. We can all just make it 1. So 2 times 1 over 1 times 1 equals n. And this is all for trial 1. So we basically get this. You do the same thing for trial 2, but the only thing that changes is now we have a lower pressure. Our pressure is now 1. So again, you can plug in arbitrary numbers and see that as our pressure went down, our moles went down. So as P decreases, if you're really looking at this in terms of formulas, the numerator I wrote all that backwards. I will fix it before I upload it. The numerator decreases because pressure went down, went from 2 to 1, meaning our answer will decrease. It went from 2 to 1. And you can do the same idea just by manipulating numbers and plugging in arbitrary values. If the denominator were to get bigger, then the answer would decrease. So as an example, if we had 1/1 and the denominator gets bigger, this is the same as 1. This is the same as 0.5. 1 is bigger than 0.5. So as our denominator got bigger, our overall answer got smaller. Okay? So that's how you can look at how measurements affect it. So that's all of the pre-lab talk. The experiment is very observation-based. You're going to watch, I think it's both me and Katie, might just all be Katie, the previous co-instructor, and we're doing 3 different pieces. We're going to look at how pressure and volume are related in the terms of density. So going all the way back to earlier in the semester, we're going to look at how heat and volume are related, and we're going to look at how temperature relates to volume. And we're actually going to cause a can to crush. Hopefully it works. And so watch the videos. A lot of it's going to be observational data. So you should have the data tables available to you. Again, any of the measured values will always fill in for you. But watch the video, figure out what happens, see what's going on, and see what you can determine about some of those experiments. Thanks, guys. Hope it was a vaguely interesting pre-lab talk.